Okay, good morning, good afternoon, good evening to everyone, wherever you are watching me from. This is Sot Tutorials, and in this lesson online, I'm just going to talk about something concerning set theory. So the set theory, this is School of Business. I'll focus on the set theory concerning the School of Business. This one, yeah. So BS 140, BEC 140, BF 140, BSP 140 of BEC. So this is a class for business mathematics. So we're talking about BS 140 class. So what are we talking about? We're talking about the concept of sets. And I'm sure this is not the first time hearing the word sets. So we run it through, starting from the definition of what a set is, and then basically from there we would see how best we can be able to understand one or two things from it. So first thing is first, what is a set? Definition. What is a set? So in definition of what a set is, the same grade 1 definition where we say a set is basically a collection of objects. That's very much correct. So in this case, I would define as a set as a set is a collection of well-defined objects. So a set is basically a collection of well-defined objects, and these objects are called elements. That's the key term there which we're talking about. So obviously there are keywords which you have to focus on. Number one is a collection there. So it means that from the majority, I don't know from where we are talking about, or wherever we are getting the things from, there are a lot of things, or maybe there are a lot of objects in that universe, but we are trying to form something which everyone, when you look at it, it can be well defined. For example, if you look at in a basket, or whatever you put in a basket, when someone is able to look at in a basket, he should be able to see something which is well defined. So if I'm able to define what is in this basket, automatically what we are simply saying that will be qualified to be called a set. So if I'm not able to define what is inside, then obviously the concept of set fails here. And I'm sure this is even an example I always even give in class. So say people's rooms, sometimes you find that they're very neat and tidy. Everywhere you look at, it is well designed and well collected. Wherever you look, you see, okay, this is maybe a locker of shoes, a locker of stockings, a locker of clothes. Everything is in place. But when you look at other people, everywhere is changanya, walanga basket here, there is clothes, there is shoes, there is there are spoons in there. You understand that person, when we were learning about sets, they were absent. Yeah, so that's the concept of sets. And then what else are we trying to talk about when it comes to sets? We have to understand that sets can be described. So every time we'll be talking about the concept of sets, we have to understand that sets can be described, and the description here will be using the set builder notation. So we'll be using the concept of the set builder notation. And apart from that, we are simply saying that we can also represent a set by listing. Represented by listing. So it's up to you to choose how you want to represent that set. Are you able to represent the set by description, which is the set builder notation, or are you representing the set by listing, which is called the roster method? So we have the concept of describing a set and we have the concept of listing the set. Which one are you going for? So for example, you find that, let's say if I want to collect a certain values of numbers, let's say a set which I'm going to collect is basically a set of numbers. What is going to happen? There are a lot of numbers in the world, so I'm trying to specifically define what I'm collecting. What kind of numbers are you collecting? Are you just collecting any kind of numbers, or the specific numbers you are looking for? Someone is going to simply say that, this is just like an example, someone is going to simply say that A is equal to X, such that X is a member of natural numbers and the same X is basically less than or equals to 6. What has happened here? This set has been described. This set has been described. Someone is just going to say, okay, A is equals to 1, 2, 3, 4, 5, 6. Is there any difference between this set and this set? There is no difference. It's just the only thing is the way the sets have been represented. So the presentation there, the first person presented the set in description, whilst the other one presented the set using the listing method. So that's what we have there. So again, we have to, the other concept we have to understand is that when it comes to notation of sets, sets are always supposed to be noted with capital letters. If you look at my description, the name of a set should be a capital letter. So it won't make sense where I'm naming a certain set as a small letter. Remember, this is a name. A name should always start with capital letters, isn't it? So this is a name of a set. So every time when I'm labeling a set, it should always be capital letters. Maybe the elements, let's say if the elements are letters, they can be small letters, yes, because they are basically objects contained in the specific set. But as usual, when I'm naming a set, I'm supposed to talk about the concept of using capital letters. So in this concept, we are going to talk about various things under sets, especially when it comes to business mathematics. But the first thing is first, when you want to understand the whole full concept of sets, basically the first part you're going to have to understand is basically understanding the terms or terminologies used in sets. The terms and terminologies which we're going to be using in sets, which is the first part. Since we understand the definition of a set, now we know what a set is. It's basically a collection of well-defined objects, and these objects, according to them, to be elements. Then what's next? We have to understand some of the terminologies we are going to be using in this concept of sets. Let's dive into the terminologies of. So when we're talking about some of the terms used in sets, we have to be very much particular, and we have to understand each and every term which we are going to be using in this topic, because we will refer to them several times. We will have to refer to them several times. So we'll start from the concept of understanding what. Number one, we'll look at equal, or we can talk about identical sets. How can we tell that two sets are equal or identical? How can we tell that two sets are equal or identical? So I'm simply saying that two sets A and B are said to be equal if and only if they have the same element. Same elements. That's the first concept there. So two sets A and B are said to be equal if and only if they have the same elements. So by the same elements, what do we mean? Whatsoever A has, B should have, and whatsoever B have, A should have. So that's what we are simply talking about. And then the concept number two here we are talking about equivalent sets. So I'll try to define them at once, then we'll look at a certain example on how we can distinguish equivalent sets from equal sets, because people tend to confuse these two. So what are we simply saying here? Two sets are equal if they have if they have the same elements, exactly the same element. Then you can simply say A is equal to B. But when it comes to equivalent sets, we are simply saying that two sets, A and B, are said to be equivalent if and only if the number, if and only if they have the same number of elements. So equivalence only focuses on the number of elements. Equal set focuses on the exact elements they have. So let's look at a certain example here we can use. So what example can I simply relate in this case? I'm trying to look at a situation where, let's say, given that A is equals to 1, 2, 3. Maybe B, I can write it in the form of 3, 2, 1. Those are two sets. So what concept can I make here? I can conclude that since whatsoever A has, B have, and whatever B has, A has, this implies that A is basically equal to B. So every element in A is exactly in B, and every element in B is also exactly in A. You can go ahead and conclude that A is basically equal to B. But when you bring in the concept of equivalent sets, what is happening? Let's say, for example, A is equal to the concept of 1, 2, 3, 4, 5, and B is equals to the concept of these are two sets having different elements. But what can I see in A? Is A equal to B? Nope, they are not equal to each other. But from the definition of equivalence, what are we simply saying? Equivalent sets two sets can only be equivalent if they have the same number of elements. So let's look at the number of elements in A. The number of elements is equals to 5. 1, 2, 3, 4, 5 elements. What about the number of elements in B? The number of elements in B is also equals to what? 1, 2, 3, 4, 5. So if the number of elements in A and B are the same, then A is equivalent to B. That's the concept. So what am I having here? A is equivalent to B. What's the symbol for equivalence? Dash to that. A equal to B. What's the symbol for equal to sign? We know the equal to sign. So if A is equal to B, then the exact elements should be contained in both. So what is happening? All equal sets basically should be equivalent. In this first term here, I can still say that A is equivalent to B. It is true. So this A and B are both equal, at the same time they are both what? Equivalent. But when it comes to equivalent for the second case here, this A and B are equivalent, but A is not equal to B. So that's the first task you have to understand. Are you able to tell when the two sets are equal or not? Are we able to tell when the two sets are equal or not? You can only tell that the two sets are equal if and only if they have the same numbers of elements contained in them. Equivalent, if and only if they, so equal if they have the same exact elements in them, but equivalent if they have the same number of elements contained in their sets. That's what we are talking about. Let's look at the second definition. So we have to understand equal equivalent set, And then from there, what is the next part which we have to understand? You can delete this. If you are still dotting down, I'm sure you'll be able to pause and dot down something. So I'm deleting. So the next term we're going to look at is basically, this is basically the universal set. I'm sure universal set, we are still having an idea what universal sets are from secondary. What is a universal set? So when you bring in the concept of universal set, this is just basically, in simple language, I mean, with business mathematics, I always just use simple language which we can be able to relate. But when I go in mathematical methods, obviously, we start using at least nice methods to use mathematically. Yeah, so this is basically a collection of all the elements in the desired sets being studied. So the universal set depends on how many sets you have at that particular time. So if I have 8 sets, if I collect all the elements in these 8 sets, put them together, I make up the universal set. From the word itself, universal, it's a universe, it's a motherboard of all the sets. So that's my universal set, which I'm going to have. So this universal set is basically denoted by a capital letter U, or you can denote it by a capital letter E in that manner. We are okay? So that's the universal set. And then from there, what do we have? We have the opposite of the universal, which we can call to be the empty set. These are simple terms which we learned in grade 1. What is an empty set? Simple language of an empty set is just basically a set with no elements in it. So this is just basically a set with no elements. A set with no elements. How do we denote a set, an empty set? So denoted by, so we denote by empty braces, or you can use the empty set symbol, which is this one. So anyone who write it in that manner, we're talking about a set which is empty. These are some of the two terms which you have to understand and familiarize ourselves with. And the last concept, or maybe the last term we can also emphasize on, is the concept of subsets. The concept of subset. So I'm trying to highlight important points so that when we start looking at some operations and solving, we shouldn't have any challenges involved there. So the concept of subset. So how do we define a subset? So definition of a subset here, we can just simply say that A is said to be a subset of B if and only if every element in A is found in B. Simple language. We've used simple language there. A is said to be a subset of B if and only if every element in A is found in B. If and only if every element in A is found in B. If and only if every element in A is found in B. So how do we denote? Denoted by A subset of B. If you look at this definition, it is just basically one-sided definition. Whatsoever A has, B should have. then A will be qualified to be called a subset of B. Now, from everything, what are we trying to talk about? For example, I can have A to be equals to 1, 2, and I have B to be equals to 1, 2, 3, 4. So what does this mean? Whatsoever A has, B have, then it will qualify to be called a subset. Let's counter check. What does A have? A has 1 and 2. Is 1 and 2 contained in B? Yes, there is 1 and 2. This implies that A is indeed a subset of B. This is very much true. But if I was to look at the other vice versa, is it true that B is a subset of A? Is it true that B is a subset of A? If I look at what B has, for B to be subset of A, everything in B should be contained in A. Is that true? 1, 2, 3. 1, 2 is found in A, but 3, 4 is not found in A. It means that this statement is wrong. What can we say? B is not a subset of A in this example. So it is from here now we can be able to break it down into something very much important, where we are simply saying that note, if A is a subset of B and at the same time B is also a subset of A. If A is a subset of B and at the same time B is a subset of A, then A and B are said to be improper subsets of each other. So if A is a subset of B and B is also a subset of A at the same time, then it is said that A and B are said to be improper subsets of each other. And it means A is equal to B. So we can also remember we had the definition of equal sets. We can define equal set as how A equals to A and B are equal if and only if A is a subset of B and B is a subset of A. Then A is equals to B. So now we've brought in the concept of improper subsets. What is the improper subset? There are two kinds of subsets here, which we have to understand. There are two types of subsets. So what we are simply saying here is, if A is a subset of B but not equal to B, then A is a proper subset of B. So the denotion will just use A subset B. That will be the denotion. But if A is a subset of B and also equal to B, then this is the same information we're talking about. A is a subset of B and also equal to B. It means that A is a subset of B and B is also a subset of A. Then A is an improper subset of B. Denoted A improper will have like a dash there like this, B. So what does this mean? The improper subset means that A and B are also what? Equal. So for example, this example I gave 1, 2 is basically one direction. What A has, B have, but whatever all B have, A does not have. Then we just use a proper. But there will be some concepts where we have A is equals to 1, 2, 3, and we have B is equals to maybe 3, 2, 1. Whatsoever A has, B have. From this concept, what am I seeing? I'm seeing A being a subset of B. At the same time, I'm also seeing B being a subset of what? Of A. Because whatsoever B has, A has, and whatsoever A has, B have. So since these two are correct, are true, therefore you can say that A and B are improper subsets of each other. As simple as that. So that's the concept of subsets. That's the concept of subset. We are okay? Yeah, so be able to jot down some questions. If any questions, any queries, you can still be able to forward to them to us in our inbox. So with this information now, at least we have been able to capture. So remember, there are already some notes which are already sent to you guys. So what are you supposed to do when you have those notes? If you have any doubt, this is where we're trying to just break those notes down for you in this video. So look at those notes and look at this video and marry them together. Automatically the concept will now blend in. So these are some of the terminologies which you have to understand. Then the other concept which we have to now bring into consideration, it is the concept of sets operations. Now let's look at set operations. Operations under sets. So under operations under sets here, what are we simply saying? We have to understand that there are three operations in sets, which we are going to break them down together here. There are basically three operations in sets. Operations, I'm trying to tell you in a situation where we're talking about how we can be able to maybe combine two or more given sets together. So we can combine them basically based on operations. So these are operations we're talking about. How do we combine two or more sets together? What operations can we use? We can be able to use three major operations in sets. So the first operation which we can talk about under sets is basically the union operation. So the union operation. Union. How do we define a union of sets? So definition of the union here is just basically the union of A and B, which is denoted by A union B, is a collection of elements belonging to A or belonging to B. So there is a key term here even which you use when defining union sets: the collection of elements belonging to A or belonging to B. That is why when you understand nicely on how these operations work, you'll be able to tell nicely without difficulties what the question will be talking about. Maybe find the number of students who took mathematics or English. Find the number of students who took mathematics or English. Or in this case is basically more used in union operations. So if this is the definition of the union, how can we write it in set builder notation? We're trying to simply say that A union B is just basically the same as saying X such that X is a member of A or X is a member of B. That's the set builder notation of our union set here. So now, if that is our union, obviously we are collecting all the elements belonging to A or all the elements belonging to B. We put them together and we call that a set. Remember, sets is all about collecting. So you collect your set. How can I join A and B together with a union? Get whatsoever belongs to A or B. You collect your set. So generally, if I was to use a Venn diagram, what remains is something of this nature. if this is my set A and this is my set B, what are we trying to collect? We are collecting everything which belongs to A or everything which belongs to B. So if I collect what has happened, I've made the A union B. So that is why sometimes when you start now bring into the concept of counting techniques with this operation, what happens? Numbers of elements in A union B in such a case will be equal to the number of elements in A plus the number of elements in B. This is in a situation where this kind of a set we have here is basically a disjoint set. These are disjoint sets. We are simply saying number of elements in A union B is equal to number of elements in A plus numbers of elements in B. But there are some cases whereby we'll be talking about concepts of joint sets, where this is my A and this is my B, where they have joined. It means that they have, when we're talking about the elements contained in A and the elements contained in B, there is something similar which they have together, the one that they are coming together in that manner. So when you bring in the concept of the counting rules, what happens from such a case? When we talk about the union, we're just talking about everything which belongs in that set. So if we were talking about everything which belongs in that set and then we bring in the concept of counting techniques, what happens? The number of elements in A union B will be equals to the number of elements in A plus numbers of elements in B. Now when we were counting for a disjoint set, it won't affect our results because these two are disjoint. They have nothing in common together. So they have, whatever A has, will count plus B, put them together, we have a union. But when we bring in the concept of joint sets, when I count the whole A, what has happened? We have counted the intersection as well. But when I count the whole B, we also count the what? The intersection again. So it is going to affect our results of the union. It won't be an accurate value. So what do we do for it to be accurate? Since the intersection, when we are counting A and we are counting B, the intersection has been counted twice. So the only way we can have proper results here is by subtracting one intersection, A intersection B. We bring it out. Then the correct value or the correct solving we're going to have will be for the union there. So with an operation of the union, we are able to count our A union B, the number of elements in A union B, by counting A and B, putting them together when it is disjoint. This is B when it is disjoint. But when it is a joint set, we are going to say numbers of elements in the whole A plus the whole B minus its intersection. Then we are well and good. So the set operations, we're simply saying there are three types of operations. The first operation we have to know is basically the union operation. What is the second operation which we have to know? What is the second operation which we have to know? So the second operation which we have to know in this case is number 2, the intersection. So under the intersection here, what are we simply saying? The intersection of two sets A and B denoted by A intersection B in that manner is a collection of elements contained in A and B. The concept here is and. That's how we define an intersection. So everything which belongs to A and belongs to B, it means we're just collecting the common items when you pick X as an element, it should belong to A and B. That's what we mean. So that element is basically in the intersection. So set beta notation, we're simply saying A intersection B is X such that X is a member of A and X is a member of B. That's what we are saying. So I'm sure we understand what an intersection means. If I was to draw my Venn diagram, this is A, this is B. Then we're talking about an intersection can only happen if the two sets are basically joint sets. So this is our intersection, which can be shaded in between there. So if that is my intersection, then the other aspect or the other concept comes in, which is the third operation. What third operation are we talking about? The third operation in this case is called the complement. Remember, there are three types of operations: intersection, union, and the complement. How do we define a complement? The complement of A denoted by A Kasipa Mwamba, or other to see A bar on top like that, is a collection of elements not in A but in the universal. So when you're making a collection of A complement, you're simply making a collection of elements not contained in the set A, but these elements can be contained in the what? In the universal set. So if that is done, then you formed a set called the A complement. So how do I write this as set beta notation? A complement is just basically X such that X should be a member of the universal set and X should not be a member of A. That's what we mean by a complement set. So these are the three types of operations under sets: a union, the intersection, and the complement. But it is under the complement where we find a baby being formed. So in the baby being formed here, we are calling this to be called the relative complement. What is the relative complement? The relative complement. What is the relative complement? So here we are simply saying that the relative complement of B with respect to A. The relative complement of B with respect to A is a collection of elements, maybe let me erase this part. So it's a collection of elements belonging to A and not belonging to B. Remember, here we are narrowing, we're trying to compare two sets A and B, but basically the joining aspect is joining set A and set B in a situation where we are trying to give a complement to B. So the relative complement of B with respect to A, it means the guy who is a complement is B, but we're giving respect to what? To A. So unlike in the first general definition of a complement, we are giving complement of A. It means whatsoever I'm collecting should not be contained in A. Obviously, if it is not contained in A, it is from the motherboard, which is a universal set. But here, instead of looking at the universal, we've narrowed our looking to be on a specific set which we are giving respect to. So it's B complement whatsoever does not belong to B. But instead of saying belongs to the universal, we say it belongs to what? The respect set, which is A. So how do we denote this? Denoted by A slash B, or you can denote it by A minus B, or you can say A intersection B complement, in that manner. So if that is the case, in set beta notation, I'm simply saying that A slash B is just basically the same as X, such that X is a member of what? A, and X is not a member of B, in that manner. So how do I shade this? If I look at this nicely, we're talking about A slash B, or A minus B, or A intersection B. Personally, it means that if this is my Venn diagram, this is set A and this is set B. If it was just saying B complement, obviously we say get everything outside B, including these spaces. But since it is with respect to A, we're talking about in the set A, exclude what belongs to B. So if this set A is somewhere up to all this far end, but since we're excluding what belongs to B, this part will be excluded. It means that A minus B is just basically this part alone. We will not touch the intersection part. So this part alone, the shaded part, is basically what? A minus B. So it is from this aspect that we have a certain general equation again, which is being formed. Remember, from the union we had the general equation, and from this aspect you can also form another form. Since the intersection is the in-between part and the A minus B is just the other part of A, this means that for me to have a complete A, when it comes to the counting techniques, the numbers of elements in the whole A can be made up of the numbers of elements with what? In this shaded part alone. What is this shaded part alone? It is the A minus B, which is A minus B plus, for the whole A to be made, it is this part plus this unshaded part. So together, this part and this part will complete the whole A. So it means that my whole A is made up of the shaded part, which is A minus B, plus numbers of elements in what? In the intersection, which is A intersection B. That's where we have another formula being formed in that manner. Or we can say that numbers of elements in B, which is this whole B, is made up of what? Numbers of elements in B minus A. What is B minus A? B minus A is this guy. So B minus A plus the intersection, numbers of elements in A intersection B. So you encounter a number of questions which might result in using all such formulas, which we are going to look at. So this is the set theory concept and the set operations concept. With this information, you should be able to solve a number of questions from the worksheet on set theory aspect. Thank you very much and enjoy your lovely day. See you in the next meeting. I'll be able to create something where we'll solve a number of practice questions involving sets. Thank you very much and have a flavored day.